Swayam Prabha. Digital India. Educated India.
Hello, welcome back to the course on Aerospace Structural Analysis. Today is the lecture 14th of the week 3. We will continue the topic that we were discussing in the last lectures, that is the torsion of thin wall closed cross section shaft. So, on the figure you can see that there is a shaft which is under pure torsional load MT and the coordinate XYZ are given. So, if I take any arbitrary cross section AA and if I plot the cross section for this particular problem that we will be discussing is a hollow thin wall rectangular cross section. The cross section is bisymmetrical, that is the upper and lower flanges are of thickness 2T and this side flanges are of the thickness T. So, this side flange, are of thickness T, this one as well as this one, whereas the top and bottom flanges have a thickness of 2T. So, the question, so this is an example problem just to get a better confidence on the theory that we have discussed in the last lecture. So, what we need to find in this problem is that this shaft which is under pure torsional moment MT, we have to find out the twist angle per length, that is theta, that we have conventionally expressed by the symbol theta. Now, how do we solve this problem? Now, using membrane analogy, if we plot the deformed shape of the membrane, if we take an arbitrary cross section of this, say capital X and capital X of the analogous membrane, and if we draw the deflected shape of this analogous membrane, then the deflected shape is going to look something like this, which is H here and H here as well. So, this is the deflected shape of the analogous membrane. That we have discussed earlier. Now, by using this deflected, so I have drawn it little bit wrongly. So, let me just correct this, because the thickness is same in both the, so this thicknesses are same. So, now, so the slopes are same. Now, what we need to find is to find theta. What we know given parameters are MT and all the geometrical dimension. Now, let us see how we can find out. Now, from the membrane analogy, we can say that the torsional moment, the expression for torsional moment can be written as twice into the volume of the deflected membrane. So, MT, that is the torsional moment, is going to be twice into volume of the deflected membrane or the deformed membrane. So, which is going to be 2 into A, into H. A is this area, mean enclosed area by the cross section. Now, if I write it in terms of the parameters given, then A is going to be 3A cross A. This is the mean area into H. So, therefore, it can be written as 6A square into H. Now, we again know that H by the thickness T is going to be equal to tau S. If the thickness is varying, then the shear stress is also varying. So, tau S can be written as H by T S. So, in place of H, we can write this as 6A square tau S into T S, T being the thickness. So, from this we can say that the shear stress tau S is going to be mt by 6A square into T S. So, this is the shear stress and this is the thickness. Now, so this is one equation that we have obtained. The other equation will be coming from the Bredt-Bethos theorem. Now, the Bredt-Bethos theorem, as we have studied, is the tau S into ds is equal to 2 g a theta. So, from Bredt-Bethos theorem that we had initially studied, we know that tau S ds is 2 g a theta, where theta is the rate of the twist angle. So, in this case, I will substitute tau S from equation 1. So, from equation 1, we can say that tau S is mt by 6A square ds by Ts, and that is going to be 2g. A is again 3A square, as we have found out. A is again the same mean area, and that is equal to theta. So, from this we can say that theta is going to be mt by 36 a to the power 4 into ds by Ts. Now, for this particular problem, Ts is varying along the thin wall cross section. So, this integral can actually be written as mt by 36a4 into. So, let us see how it happens. So, for this portion A, I have the thickness of T. So, it will be 2A by T, or let me write it in longhand, so for better understanding. So, we can say that for this portion, as we are moving, for this portion ds by Ts is going to be A by T. Then for this portion, as we move along this portion, then this is 3A by the thickness, which is 2T. And then again, as we move along this section, this is A by T. Similarly, as we move along this portion, this one is 3A by 2T. So, if we calculate this, if we simplify this, then this is mt by 336. Sorry, I have missed the g. So, there will be a g here, this is 36. So, 36 g a to the power 4, then I have 2a by t plus 3a by t. which is equal to mt into 5a by 36 g a to the power 4 into t. So, a will cancel out, this will become a to the power cube. So, this is what we have. So, therefore, the final answer can be written as theta is equal to mt by 36 g into a cube into 5. So, this is the answer that we get for this problem. So, that is how we solve this example problem when we need to find out the rate of twist of this thin walled hollow rectangular cross section shaft by using the principle of membrane analogy. So, let us move into the next problem, where we will handle slightly more difficult problem of torsion of hollow thin walled shaft, but unlike the previous problem, here the shaft has multiple cells. So, this is the top figure is the cross section of a shaft under pure torsion. Let the torsional moment be empty. Now, it has two cells instead of all the previous cases where we have dealt with only one cell. This one has two cells. So, let us call this as cell 1, and let this area, this mean area that we have, let us call this mean area to be A1 and this mean area to be A2. The two area enclosed by the two cells of the shaft. Now, let us see the thickness. The thickness of this portion, let it be uniform over this portion and let it be T1, and let the thickness of this portion be equal to T3, and the thickness of this portion, uniform thickness, is T2. So, let all these thicknesses, so T1, T2 and T3, though I have not drawn them to be uniform, are uniform thicknesses. We can also do with variable thicknesses, but generally in real life cases the thicknesses are uniform. So, let these two junctions that we have between the two cells, let us name them as K and J. So, now let us see if we can handle this problem and find out the torsional behavior of this shaft with this particular cross section using membrane analogy. Now, if we imagine an analogous membrane and we draw the deflected shape of the membrane, then the deflected shape is going to look like this. So, this is the section XX. So, this is the deformed analogous membrane. Let me draw the coordinate axis. So, this is the x axis, this is the y axis, and so similarly this is the x axis and this is the z axis. Now, we can see that since each leg of the cross section, that is, this is, let me call this as leg 1, this as leg 3 and this as leg 2. So, each leg of the cross section has a different thickness, and now if you can visualize an analogous membrane of this shape and this hollow portion is replaced by a flat plate, then you can visualize that the deformed shape of the analogous membrane will look like this, and this height, let me call them as H2, let me call this height as H3 and this height as H1. You will be probably able to appreciate that since the cross section has two hollow regions, or we call it two cells, then the deflected shape of the membrane will, because it has two cells, the deflected shape of the membrane will not have a single depth h, rather it will have multiple depth, which is H1, H2 and H3, where H1 is equal to H2 plus H3. Now, we can say that tau 1, that is the shear stress in the portion 1 or leg 1, can be written as H1 by T1, or in other words, tau 1 T1 is equal to H1. Similarly, I can say that tau 2 is going to be H2 by T2, or we can say that tau 2 T2 is equal to H2, and so on. Tau 3 is going to be H3 by T3, or tau 3 T3 is equal to H3. This is exactly same as what we did in the earlier lecture. Now, since we have all these three relations between the shear stress, the thickness of the portion and the depth of the or height of the deformed membrane, then we can say that H1 is equal to H2 plus H3 from geometry. Therefore, this can be written as tau 1 T1 is equal to tau 2 T2 plus tau 3 T3. This we can write. Now, again tau 1 T1 is nothing but Q1 and tau 2 T2 is Q2 and tau 3 T3 is Q3. So, Q1, Q2, Q3 are the shear flows in portions 1, 2 and 3. Right. So, this is what we get from the membrane analogy. Now, let us try to conclude what we have understood from the membrane analogy and what are the inference about the mechanics that we can make from this membrane analogy. The first conclusion that we can make is that the shear flow Q, which is given as the product of the shear stress into the thickness of the portion, does not vary in a portion between any two junctions. So, for portion 1, I have a single value of the shear flow. So, we can say that no change happens to the shear flow in the portion between two junctions. That is the first inference that we can make, because each portion is going to have a single h, and so h is constant. So, over this entire portion that we have, this portion 2, because it has an uniform thickness T2, I will have an uniform depth of the deformed membrane H. Therefore, the shear flow here, which is going to be H, which is tau into T2, is constant, is a single value for this entire yellow colored portion. So, the shear flow is not going to change in this portion. This is true even if this thickness T2 is varying. Here for this particular problem I have considered T2 to be uniform, but even if T2 is varying, Q2 is going to be constant in this portion. So, we can say from membrane analogy, because Q2 is analogous to H2 and there will be a single H2 for this yellow portion. So, we can say that even for varying thickness tau 2 T2, the shear flow is going to remain constant over this portion 2. So, same holds for portion 3 and portion 1. So, we can say that for this particular case, we can say Q1, Q2 and Q3 are constant. It is not going to change in the portion. Okay. The second inference that we can make is that Q1 is equal to Q2 plus Q3. So, what is meant by Q1 equals to Q2 plus Q3? So, let me draw, say this is Q1. So, this is Q1. This is the direction of the shear flow Q1. So, then I can say, and this is Q2 and this is Q3. So, what does Q1 equals to Q2 plus Q3 means? It means that the input at any junction the input shear flow is equal to the output shear flow. Right. So, at junction J, the input shear flow is Q1, which is equal to Q2 plus Q3. Similarly, at junction K, the input flow is Q3 plus Q2, the output is Q1. So, Q1 is always equal to Q2 plus Q3. Therefore, it is convenient to imagine shear flow as a fluid flow, and we know that at any junction between pipe, the input fluid flow has to be equal to the net output fluid flow from the junction. So, the same condition holds for shear flow when we are dealing with torsion of shaft with multiple cells. So, these are the two important inference that we can make from the membrane analogy of torsion of thin walled cross section. Now, let us see once how can we solve for Q1, Q2 and Q3 and therefore get the value of tau 1, tau 2 and tau 3. So, from membrane analogy, we again know that the torsional moment MT is nothing but 2 into volume of the deformed membrane. So, for the what we can write with the deformed the volume of the deformed membrane for this particular cross section can be written as 2 into A1 H1 plus A2 H2. we can always say this, that it is going to be A1 H1. From geometry we can say that the total torsional moment is going to be 2 into A1 H1 plus A2 H2. Now let us see what we can do further to it. So A1 we will know H1 is going to be tau 1 into T1 and H2 is going to be tau 2 into T2, or this can be written as 2 into A1 Q1 plus A2 Q2. So this is the second equation that we get. Now let us use Brett-Bathos theorem. So from equation 2 we have seen that if we can find out the value of Q1 and Q2, then we can express Q1 and Q2 in terms of the applied torsion moment mt. Now let us see how we can solve for Q1 and Q2. So let us use Brett-Bathos theorem, that is tau into ds is equal to 2GA theta. Theta is being the rate of angle of twist. Now how do we apply this? Now this tau ds equals to 2GA theta can be individually applied for each of the cell. So I can apply Brett-Bathos theorem for cell 1, I can apply Brett-Bathos theorem for cell 2. So if I do that, then I can write this as tau 1 into S1 if this length is S1, if this length is S2, S3, and if this length is S2, then we can say that tau 1 into S1 plus tau 3 into S3 is going to be 2GA1 and theta. So for cell 1, okay. So for cell 1 it will be tau 1 S1 plus tau 3 S3, and that is going to be 2GA1 theta. Now similarly we can apply it for cell 2, and we can say that tau 2 S2 minus tau 3 S3 is going to be 2GA2 theta. Okay. So the only thing that you have to keep in mind is that you have to move in one direction. You have to take one direction to be positive. So if we are moving in this direction, then I have tau 1 into S1 plus tau 3 into S3. See, all these two shear flows are in the same direction. Now if I am moving in cell 2, then we see that tau 2 S2 is in one direction, is in clockwise direction, whereas tau 3 S3 is going to be in the negative direction. So that's why I have put a negative sign. So I have this negative sign because of that. So from these two equations, so this is another set of equation that I have. I have equation 3 and equation 4. Now from I know all this, I know A1, I know A2, I know S3, I know S1, S2. So I can solve this equation, and I can use the first equation, which is Q1 equals to Q2 plus Q3, which is in turn tau 1 into T1 equals to tau 2 into T2 plus tau 3 into T3. So this is my equation 1. So from this 3 equation I can solve for tau 1, tau 2 and tau 3. Now, once I solve for tau 1, tau 2, tau 3, I can also solve for q1, q2 and q3 just by multiplying it with the respective thickness. And once I get this, I can substitute this and solve for MT. So, all this will be obtained in terms of theta, and therefore, if I plug this in, I will get MT in terms of theta, and thereby I will get the torsional rigidity. So, in the next lecture, we will solve an example which will clarify this even further. Thank you.